This is Philip Metzger. I apologize I couldn't be there. I came down with COVID the night before I was supposed to travel to Denver, so I cannot travel. I'm going to be talking by video recording about the economic modeling of the competitiveness of lunar water over Earth-launched water, including a number of economic considerations. The motivation for this is that launch vehicles are lowering the cost of launch. And there are people making claims that it's cheaper to launch water from the Earth than it is to mine it on the moon. And these claims need to be rebutted. So I'm going to make it quantitative by discussing optimization of reliability, the experience curve, also known as Wright's law, economies of scale, economies of scope, and I'm going to give you the results. Now, I'm not just going to be hand waving, I'm going to rely completely on real industry data to quantify all of these effects. Optimization of reliability. NASA pays a very high reliability penalty because of the national reputation of our space agency. But commercial space has to optimize for profit. And the way that it reduces, the way that we can reduce the cost by reducing reliability is well known. It's well known that testing for reliability drives the cost. There's the rule of nines, very well known in reliability engineering. There's a saying in NASA that the last 10% of reliability is 80% of the cost on space missions, or some version like that. But we do have empirical data from industry. We don't just have to rely on sayings. There's a model, for example, by Metis, and it was applied by Stancliffe and coworkers to lunar rovers. This model is based on actual industry data on the cost of reliability. I don't have time to go over the details, but I'll be glad to send you the details if you request. Okay, so if you plot the cost factor on reliability, it looks like this. And you see above 80% reliability, the cost explodes. And you'll notice the the y-axis is powers of 10. But there exists an optimum reliability. If you make a system too unreliable, then you have to build too many spares and you have to pay the cost of shipping all those spares to the moon. And so this cost of shipping spares dominates. On the other hand, if you try to make it too reliable, then you don't need a lot of spares, but the cost of reliability, building that one single platinum-plated unit, drives the cost. And so there is a reliability optimum. That reliability optimum depends on the transportation cost. So when the transportation cost is $10 million per kilogram to the lunar surface, you want to build systems that are like 94% reliable. This is, I'm using a 5-year window of operation on this. But if your transportation cost goes down to about $10,000 per kilogram, then you're going to want a system that is going to fail 2/3 or 1/3 of the time over the operational period, but so that you can just replace it because you actually save money that way. Okay, second of all, the experience curve. Based on centuries of industrial data, we know that production costs drop as we gain experience because of management organization, of capital assets becoming higher technology, labor becoming more skillful, the supply chain being better organized. And economists have measured this and fit it to curves, and this curve is known as Wright's law, which says the integral over the production rate gives you the total quantity produced up to a point of time divided by your baseline total production, and then raise that to a powered log base 2 of B. That tells you the factor on the cost of producing the next unit. And B is the factor that your cost will be after you double your production. So every time you produce 2 times as many more, if B is 0.75, then when you produce twice as many widgets as you had before, the cost now goes down to 75% of what it was before. And every time you double the number of widgets, the cost goes down to 75% of what it was the previous time. And this is the empirical experience of industry. We're not making this up. Second of all, there's economies of scale. The production cost is less when an operation is larger in general because of geometric scaling and other efficiencies that you can leverage. And this is not the same as the experience curve. You can have a very experienced team build a small factory and a big factory, and the big factory will have a lower production cost because even though they have the same experience in both. So there's these are distinct factors. There's also an empirical equation based on industry data, which describes economies of scale, and it says the production rate of a factory divided by the baseline raised to an exponent is the cost factor of production. And A is typically between 0.2 to 0.85, but when you weight over industry, it's about 0.66. So I'm going to use industry average. I'm not claiming anything special here. I'm going to say, what if lunar industry is no better than average? Okay, there's also economies of scope, additional business activities which support your asset skills and processes to gain experience and scaling efficiencies in addition to or on the side of your main business. And these can contribute to lowering the cost as well. And so I don't really have time to go over this, but it's in the abstract. But you can manipulate the equation and get some insight. And basically, it turns out that operations cost is going to be the main determinant rather than hardware fabrication cost or even the transportation cost. Okay, now what are we comparing against? Earth-launched water. The optimistic projections are that it's going to go down to $30 per kilogram to LEO. And I'm going to assume that happens over 30 years, and at the end of that period, there's one Starship launch per day. And this is typically what people claim will have to happen to get the launch cost that low. And I think that's actually very feasible. I think that can happen. I think Elon does have a good business case for settling Mars, but that will be a talk for another day. So using the normal industry average economies of scale, it turns out that if they only have a learning curve exponent of 0.92, then that's $30 per kilogram is what you would expect them to achieve at that launch rate. So this is not actually that aggressive. This is not overly optimistic. I think this is a little bit sub-optimistic. So I think we actually will get there. Now the pessimists who don't believe in space resources, they'll say, well, let's compare the costs. But if you look at what they're doing, they'll compare the cost where lunar water has to use the current transportation costs, like $300,000 per kilogram to the lunar surface. But they will assume a super low launch cost for the Earth launch water based on future rockets coming out from commercial space companies. And second of all, they will assume that the lunar extraction system costs and the ops costs are based on studies done for NASA with the reliability premium built into it. But then they will assume that all the operations and the depot activities for commercial will be based on the commercial practices. So we're going to deconstruct that so they can't get away with those dishonest arguments anymore. But if we do allow those dishonest arguments, I want to show you that, first of all, the third mistake they make is they only compare current estimated prices year one. And so they'll say, when I put in those pessimistic assumptions, this is the plot you get where the lower axis is the delta V from low Earth orbit. The vertical axis is years from the start, and the color tells you the cost of water. This dark dashed line demarks where it's cheaper to get the water from the moon on the right and it's cheaper to get it from the Earth on the left. And you can see the slope of the line changes along that solid dashed line for that reason. And the color tells you the cost of water from whichever source is cheaper at that delta V from the Earth and at that time from the present. And so you see when you look at year one, they'll say, look, aha, lunar water, it's only affordable out to low lunar orbit, but you can't really use it for anything beyond there because Earth water is cheaper. But if they only looked to year two, lunar water is already cheaper at the Earth-Moon Lagrange points, according to the economics equations. And if you go out to year 12, lunar water is cheaper all the way to geostationary transfer orbit. And this is using the pessimistic unfair assumptions. Let's get rid of those pessimistic unfair assumptions. Oh, but first let's talk about comparative advantage. Lunar water doesn't have to beat Earth water to be the water of choice. It just has to be close. So for example, in year 20, using these pessimistic assumptions, in year 20, lunar water will cost 20% more than Earth water. But if Elon wants to launch a Starship to Mars, he has to launch 8 more Starships of water to refuel it. Or he could buy lunar water at a 20% premium. And by doing that, every Starship can be used to send people to Mars rather than 1 out of 9. So he can increase his value of his company by a factor of 9 by paying only 20% more. And that's the result of comparative advantage. And so lunar water doesn't have to beat Earth water. It just has to have a comparative advantage. If you can make water on the moon relatively cheaper than you can send colonists to Mars, whereas Elon can send colonists to Mars with relatively more value than launching water, then it makes sense to buy the lunar water. Okay, so in this study, I'm going to use aquafactorum, which is a lunar mining method that I worked on a couple years ago for NIAC. Don't have time to go over the details, but it's a starter system, a very small starter system. It does not have economies of scale, but it's designed to be something you can start with right away. And using this system, even using unfair launch costs, this system uses so much less energy than a thermal mining system that it's cheaper to take the water from the moon all the way out to geostationary transport orbit in year 1. And this is consistent with what we studied in the NIAC study. In the NIAC study, we only looked at year 1, but look at this. By the time you get out to year 12 or 13, lunar water is now cheaper all the way down to low Earth orbit. But we can do better than that. Let's use Starship launch costs to take all the aquafactorum hardware to the moon, rather than using the expensive transportation. So now we're comparing apples to apples. It turns out that lunar water is cheaper to low Earth orbit by year 2. So you get much more advantage when you compare apples to apples. But we can do even better. We can use water-based electric thrusters to deliver the propellant. And so I put in a discount rate. It turns out it didn't have hardly any effect, but I did do it just to see. And so because the longer transit times, there's a cost of money involved. And it turns out you can get the cost of lunar water vastly cheaper at low Earth orbit than by using Starship to ship everything around. When you look at the relative cost of lunar water versus Earth water, this plot here is lunar water minus Earth water at each location in space. And you can see that by 30 years in the future, lunar water is 50% cheaper than Earth launched water, even in low Earth orbit. And this is not using crazy numbers. This is using industry average experience. Okay, if you think this will not happen, then you're claiming a miracle that violates everything we've ever observed. And you need to justify that, because what I'm showing you is just what you normally expect to happen. Okay, now instead of using aquafactorum, we could use the study by Charania and De Pasquale. They had a reliability premium. Their ops cost was very high, for example. But when Starship or reusable launch people, ISRU pessimists talk about the study, they'll say, aha, lunar water isn't even cheaper in low lunar orbit. This is the result of the Charania and De Pasquale study. They'll say you can only use it on the lunar surface. But again, that's comparing apples to oranges on the launch cost. So if we modify the Charania study to use the same transportation, apples to apples, it turns out within just a few years, even with these high expensive systems, lunar water is cheaper all the way down to GTO. But we can do even better if we use electric propulsion of the lunar-derived water. Okay, finally, economies of scope. I don't have time to really talk about it, but if you had metal making on the moon and you're boosting space-based solar power, then and I'm assuming these don't kick in until year 10, but look at how rapidly the cost drops in cislunar space because of the economies of scope. And you get ridiculously cheap prices of water. But why not? Those ridiculous price drops are the kind of thing we see in other industries here on the Earth, and I think it can happen in space as well. So, conclusion, let nobody say that low launch prices will drive cislunar space resources out of business. The cost of cislunar space resources drops faster than the cost of launch, and therefore space resources are the future. Thank you so much for your attention.